Today we're going to be looking at Lagrangian dynamics, which is another way of finding the normal modes of a system. And it's very useful in more complicated problems, where we have lots of degrees of freedom. So the Lagrangian is defined as the difference between the kinetic energy T and the potential energy V. And the Lagrange equations of motion are written as follows. Now we will offer these without proof, and we will just use them and show that we get the results we had earlier, which will act as confirmation of these. So the time derivative of the partial of L with respect to x dot. Now we're looking, say, at a one-dimensional problem, then x dot will be the velocity. That is going to be the partial of the Lagrangian with respect to the position variable x. Now let's just show that these equations, these Lagrangian equations, are equivalent to F equals ma by considering the absolute simplest problem, just the mass on a spring. So the kinetic energy, and again we're using T for that, that's half mv squared, but in one-dimensional problems, of course, v is just dx dt, or x dot. So that's x dot squared. Elastic energy on a spring, again we're using v for potential energy, is half kx squared. And so the Lagrangian is the difference between those two. So it's half of mx dot squared minus half of kx squared. So let's see what this Lagrangian, these Lagrangian equations will tell us in this case for this Lagrangian. So first of all, we have to do the partial of L with respect to x dot. So this is on the left-hand side of Lagrange equations. And so we're differentiating with respect to x dot, half mx dot squared plus half kx squared. Now, x and x dot are independent variables. So with the derivative with respect to x dot of this term is just 0, and we just differentiate this with respect to x dot. So that will just be a half m times 2x dot, or it's just mx dot. Now for the Lagrange equations, we still have to do the time derivative of that. And after we do the time derivative of mx dot, we get, of course, mx double dot, the second derivative of position. Now what's on the right-hand side of the Lagrange equation is the partial with respect to x of the Lagrangian. Now this first term depends on x dot, so it will give a 0 derivative when we take it. We'll only get something from the second term. Differentiating this with respect to x, we're going to get minus kx. And so the Lagrange equation in this case reduces to mx double dot is minus kx, which is, of course, the equation for a mass on a spring. So if this was the spring, this was the equilibrium position. If the mass had been moved over to location x, perhaps it's connected at this end, and then it's moving on a frictionless surface, then, of course, there would be a spring force, kx in the negative direction, that was making this accelerate. And so this would be exactly the force equation for that system. So, as we're making the claim here, these Lagrange equations are a way of getting to F equals ma when that may otherwise be quite difficult, and therefore they're a way of finding the normal modes of the system. Now, that's a little out of place. Here we go. This is where we want to be. Why is this a way to get to the F equals ma equation? So this is sort of offered as like a plausibility argument for the Lagrange equations. Well, if we do the time derivative of, this is like a velocity derivative of the Lagrangian. So the Lagrangian in general is going to be velocity half mv squared and then minus some potential energy. So earlier we had this as elastic potential energy, but we're going to consider a variety of problems, so this could have a bunch of different forms. But when we do the x dot derivative, if the velocity only depends on x, then of course the x dot, or the velocity derivative of this term, will be 0, and you're just going to get, as we had earlier, the x dot derivative will just be mx dot, and after you do the time derivative, it's mx double dot, which in one-dimensional systems is, of course, the acceleration. Now on the right-hand side of the Lagrange equation, when we do the partial with respect to x of the Lagrangian, oops, started to write v squared there, but I should keep it as x dot squared. Now the x derivative of this kinetic energy term just disappears, and so what we end up with is just negative the partial of the potential energy with respect to position. But of course, as we showed earlier in the course, for a conservative force defined by potential energy, the negative gradient of the potential energy is the force. So the Lagrange equation, which says these two are equal, left side equals right side, is just saying F equals ma. Now, the Lagrange equation also leads naturally, in systems with more degrees of freedom, to matrices which can then be set up to find the eigenvalues in the normal modes. Let's look at another problem. We did this one as well. A pendulum with an elastic cord. Now we have two variables here that define the position, the location of the system. So first of all, there's the angle theta of the pendulum, and then the distance x, which was the extension of the spring. So the extension of the spring. So the pendulum the string at its rest length would be L, and then it has an extra stretch x. And of course this is the overall length of the cord, and that's going to vary as it moves, right? So L is a constant, but x can increase or decrease depending on what's happening to the spring. Now, so this is a mass m. In the r hat theta hat coordinate system, the kinetic energy will have two terms because the velocity can have two terms. So first of all, you're moving in the angular direction as the pendulum swings, but you can also be moving outwards. The spring can be stretching a little bit. So we're going to have two terms in the velocity, and these are just the common terms we had for velocity in cylindrical coordinates. So this is the radial velocity, and this is the angular velocity. Now, L is a constant, so if you do the time derivative of r, you just get x dot, where x in this case is the stretch of the spring. And now r, that distance, is L plus x. This will be theta dot as per the equation, and that is in the angular direction. Okay, so when we do kinetic energy, it's half m. Now these two components are perpendicular to each other, so the square of velocity is just going to be the square of the two components. So there'll be x dot squared, and then there'll be the square of this component as well. L plus x squared theta dot squared. Okay, so there's the kinetic energy, right? And maybe I'll just put the coordinate system on there. There's the outwards radial direction. There, perpendicular to it, is the theta hat. Oh, sorry, theta hat actually goes this way, in the direction of increasing theta. There's the theta hat, angular direction. All right, so that is the kinetic energy, and we're going to stick that into our Lagrangian shortly. We also need potential energy, and it's suggested to us that we give potential energy relative to h equals 0, 0 height up here at the ceiling. And so the height of the particle at the instant shown is this distance right here. That's L plus x times cos theta. And that'll be negative height. We're below the zero of potential energy. So it's going to be mgh. And that's a really awkward way to write it, so I'll just pull the minus sign out in front. And there we go. There we have an expression. Oh, and I forgot the elastic energy. So we have height energy, and of course, once the pendulum cord is stretched a little bit by a distance x, it just acts like a spring, so we also have elastic energy in there. All right, so now we build our Lagrangian. L is t minus v, and this has already been set up for us on the next page, so we just recopied that kinetic energy. Two terms, depends on x and theta. And the potential energy also depends on x and theta. And now, for this two-variable system, there's going to be two Lagrangian equations. One that's with respect to x dot and x, and another one down here that's with respect to theta dot and theta. And we'll need to construct both of these. So, trying to write small here, so this will be the d dt. Now, when we differentiate this with respect to x dot only appears here, so again, we're going to get 2 halves mx dot, or just the d dt of mx dot. So as we did before, that will just be mx double dot after we do the time derivative. All right, so now let's go to the right-hand side, and we're going to differentiate this Lagrangian with respect to x. So we don't get anything there, but we get something from this term, and from this term. So the first one, using the power law, so it'll be a half m, then we're differentiating L plus x squared. So the 2 comes down, L plus x, and then we don't do anything with the theta dot squared, it just stays there. Then we differentiate this with respect to x, the L term's constant and disappears, so we just get mg cos theta. And finally, when we differentiate this with respect to x, we just get minus kx. Okay, so simplifying a little bit then on the right-hand side, the 2's obviously cancel out, so we get m L plus x theta dot squared, and then again the mg cos theta minus kx, that is still there. And just to rearrange this a little bit, to put it in a more familiar form, I'm going to bring this term over to the left-hand side. So I'm going to get mass, factor that out, it's going to be x double dot minus L plus x theta dot squared. And then the other stuff is just left over here, mg cos theta, subtract kx. And the reason we do that is that it should now be familiar to us, because this is the acceleration in cylindrical coordinates. X double dot minus the radius times theta dot squared. And this side is actually the sum of the radial forces, because we're going to have, and that's what this little force diagram is, we're going to have a little kx elastic force from the pendulum cord. And then this force is mg, and you can see there's an outwards mg cosine theta component. And so the net radial force, the radial direction outwards, is mg cos theta minus kx. And of course, by Newton's second law, that has to equal the mass times the radial acceleration. So this is again just pointing out that, hey, this thing that we're doing with the Lagrangian is giving us back Newton's second law. So eventually we'll go to some problem where, it's really tricky to write these equations out with Newton's second law, and the Lagrangian approach will just speed things up for us. So that was the first variable with respect to x. We also had theta dot and theta to consider. So on the left-hand side, so we're going to have a time derivative, d dt, that's a normal Cal1 derivative, and then we're doing the partial eval with respect to theta dot. So this is the only time we see a theta dot term. So we're going to have a half, and then it's mass L plus x all squared. That's untouched, and then the theta dot derivative is just going to be 2 theta dot. Now it remains, of course, to do the time derivative of this. The 2 and the half disappear. The L plus x, well, you see now both x and theta dot depend on time. So we'll have to do the product rule. So we'll leave the first term alone and do the time derivative of theta. That'll be theta double dot. And then we'll leave the theta dot alone, and we have to do the time derivative of this. So the m is there. So we're doing time derivative, so the 2 will come down. But then, of course, we need to multiply by the derivative of the inside, which is the time derivative of x, which is x dot theta dot. Okay, and then that completes the... Oops, didn't want to move that. I want to move this guy over if I can. Just give myself a bit more room here. So that completes the left side of Lagrange's equation, and now we need to work on the right side. which is the partial of L with respect to theta. Okay, now theta only appears here, so that's pretty easy to do. It's just the derivative of cos theta with respect to theta. And derivative of cosine is minus sine, and so we get that term right there. Okay, that's not going to change, but I'm just going to factor out an m here. And then I'm going to also notice that L plus x, well, maybe I will write this. Sorry, I lied. L plus x, and then I need room for the sine theta there. Again, that seems to want to move. But what I'm really trying to do is move this. Sorry for the delay. There we go. So now I can stick the sine theta back in there. And what I'm going to do is I'm going to divide through this whole thing by L plus x. That's the first change I'll make. And the second change is I'll factor out the m on the left-hand side. So dividing by L plus x, I'll still have an L plus x left here. This L plus x has gotten factored out already. So did the m. So that's just 2x dot theta dot. And then when this L plus x gets factored out, it's just minus mg sine theta. Now if we go back to our force diagram, the mg sine theta is in the negative theta hat direction, because theta hat direction of increasing theta would be going this way, and mg sine theta is opposite to that. So that is the net angular force. That equals the mass times the angular acceleration, and this is r theta double dot plus 2 r dot theta dot, which you may recall is our expression for the angular acceleration. Okay, so the Lagrange equations have again basically given us back f equals ma in this unfamiliar problem of a stretchy pendulum. So what we're going to do then is stop at this point, and then in class we'll come back to a problem that took us a little bit of time, which was the coupled oscillator, and we'll see what Lagrange's approach, the Lagrangian dynamics approach, can do for us in this case. And then we'll consider a variety of problems after that, where Lagrangian dynamics is a useful technique.